Hello, my name is Rob Reynolds. Welcome to Calculus section 4.6. Today we're going to get two theorems, the mean value theorem and Rolle's theorem. We're going to start with Rolle's theorem. Rolle's theorem says that if we have a function that's continuous and differentiable, meaning no holes, no gaps, and you can take the derivative at every point within the interval, then there must be some max in between 2 points if f of a is equal to f of b. So a is the beginning of the interval and b is the end of the interval. If it's a smooth continuous function, there's got to be some place where the derivative is equal to 0. Usually, not always, we let f of a and f of b, they have to be equal to some y value. The y value that we usually let them be equal to is 0, although you don't have to be. But it's the easiest way to find two y values or two x values is by just going for the roots. So it'd be easiest just to let the function cross the x-axis because we're used to setting functions equal to 0 and finding intercepts. But remember, Rolle's theorem only works for continuous functions, and here's a continuous function, but it's not differentiable because the slope here is undefined. It's a vertical line. So as the slope approaches, if you remember, we've got an undefined slope. So it has to be continuous and differentiable at every point. So example number 1 says, let's go find a place. Well, since it's a polynomial, then I know that it's continuous and differentiable at all points of the interval, but they don't give us f of a and f of b. So let's go find an a and a b that we can say that the y values are equal. And again, like I said, the easiest thing to do is go for the zeros, although you don't have to. Let's go find zeros by setting this function equal to 0 by quickly factoring. Factors of 10 that add up to 7 are 5 and 2. And I get x is 0, 5, and 2. Now I could pick any interval here because Rolle's theorem says I'm going to pick the largest interval between 0 and 5. I could pick the 0 and the 2. I could pick the 2 and the 5. There's going to be a max or a min in all of those intervals, and I'll show you a graph of this in just a moment. I'm going to choose 0 and a 5. I might find more than one max or min. So now that I've found my 0, 5, I'm looking for some value between 0 and 5 that causes a max or min. And to do that, all I have to do is find the derivative and set it equal to 0. So the derivative is 3x squared minus 14x plus 10. Now I don't think that factors, so I'd have to use the quadratic formula. And after doing so, it's approximately, if you used a calculator and guess left, guess right, guess on. So here's the exact answer if they ask for that. Here's some approximations if I used a calculator. And so what it's saying is at these x values, there's a max or a min. So Rolle's theorem again states that there's at least one point in this interval. We're going to call that point C. Well, we found 2 points, 0.88 and 3. So Rolle's theorem says there's at least one point such that there's a max or a min. Remember, to find maxes or mins, we just take the derivative and set it equal to 0. So looking at the graph of this, you can see at 0.88 the slope equals 0, and then at 3.79 the slope of this function also equals 0. So again, what you would demonstrate for me is that you would check Rolle's theorem to make sure that it's continuous and differentiable. Then you would find an interval so that the function, the y value equals 0, or two values, f of a and f of b have to be equal, not to 0, but they have to be equal. and then it's usually nice to let it equal 0. And then once you do that, just take the derivative set equal to 0 and tell me the max or the min. The mean value theorem states that the slope of the secant should equal the slope of the tangent. And to find the slope of the secant, we do this formula here, f of b minus f of a. Well, it's just the same slope formula that you did back in your Algebra 1 days, y minus y over x minus x. It's just now we have, instead of x minus x, we have an interval, an a to b interval. So that's why we're doing b minus a. So remember, that's just y minus y over x minus x. It's just the slope that you're familiar with. But the slope of the tangent we've learned now, that's the derivative. So if the slope of the secant, which crosses twice, is equal to the slope of the tangent, which only has one point of intersection, then, well, it's got to be continuous and differentiable on that interval again. There's at least one point such that the slope of the secant will equal the slope of the tangent. So that's the mean value theorem. If you've printed off the PDF file and are following along, I'm going to skip example number 2, but I would encourage you to go through it. They actually kind of give you the derivative here, and it's kind of an easy example. So I'm going to go on to example number 3, and I'm going to actually go find that the slope of the secant, where the slope of the secant is equal to the slope of the tangent. So the slope of the secant really is this f of b minus f of a all over b minus a, and they gave me an interval, a to b. So I'm going to do f of 2 minus f of negative 2 all over 2 minus negative 2. I'll continue evaluating that, 11 minus negative 9 over 4, and come up with a 5. I'm going to say 5 has got to equal the slope of the tangent, which we know as the derivative of the function. So I'm going to go back up here, and find the derivative of this function. So the derivative is 6x squared minus 3. And I'm going to set that equal to 5. So 6x squared equals 8. Dividing through by 6 and reducing gives me 4/3 is x squared. And then, of course, x would equal plus or minus 2 over the square root of 3, which you could simplify to around 1.15 and negative 1.15. Now, this actually said find the points, and usually we let points be some ordered pairs, x and y. So you can use the exact values, but if we use 1.15, I'll just go back to my graphing calculator and punch in this function and find this y value. And that y value turns out to be around 0.59175, and for the negative, around 1.4. So again, what we did is we found some place that the slope of the secant is equal to the slope of the tangent. It looks like the author just said, well, just plug that back in. They didn't actually find the y values here, but they did get the same x values. So let's see if they drew a graph. Sure it is. Negative 1.15. So this point, the height here, the y value, I think is around that 1.4. And then this y value, you can see it's really close to 0, but it's closer to 0.59, half. So they don't have any scale on the y-axis. We don't really know. But what's happening in the mean value theorem, here's the secant crossing more than once, and we found some x value that the slope of the secant's equal to the slope of the tangent, and it happens to happen at 2 different places, negative 1.5 and 1.5. So we actually found those points, ordered pairs. And that's basically a lesson for 4.6. These are just some reviewing things. You already know that if you take the derivative and set equal to 0, you'll find a max or min. But if that happens at all of the points, then that must be a constant function. In other words, the graph must just be a horizontal line because everywhere you go, that's the slope is 0. So you must have a constant function. And then they go through and they give you some other theorems that I think you feel pretty comfortable with. If the first derivative is greater than 0, then it's increasing. If the first derivative is less than 0, of course you know that that means decreasing. I hope you know that by now. So just a quick review before we end this video. Rolle's theorem, you have to check to see if it's continuous and differentiable. Otherwise, it doesn't even apply. So continuous, yeah, this graph is a cubic graph and it's shoved up 1 unit. It probably looks, I don't know, you can graph it, just see if it's continuous. But I'm only interested in the interval from -1 to 1. So I think it's continuous. Differentiable means if I find the derivative of this thing, well, the derivative of 1 is just 0. The derivative of this is -2/3 x to the -1/3, which you could write as -2/3 to the 1/3. And all of a sudden I see, ooh, if x is 0, this function's undefined and 0's in that interval between -1 and 1. And so I would say it's not differentiable over all of those points in the interval. So because I can't find the derivative at, so since f prime 0 equals undefined and 0's in this interval, I would say this one is not determined. I can't apply Rolle's theorem to this. Let's see what the author says. Yeah, does not apply. It doesn't even exist. The first derivative doesn't exist at 0, so it's not differentiable, and so that's the it. You could go ahead and Rolle's theorem still might apply. You might be able to find a point that is a max or a min, but we're not guaranteed that it would apply. And then the mean value theorem, again, just kind of reviewing a little bit about derivatives of inverses. Now, we'll remember inverse functions are defined between what? -pi/2 and pi/2 for sine inverse and tangent inverse. So the first thing I say is, yeah, it's continuous on this interval between 0 and 1/2. Let's find out if it's differentiable. The derivative of this thing, hopefully you have these memorized, is 1 minus x squared. We derived that a couple of videos ago. And so it looks like all the points between 0 and 1/2 could be plugged in there and it will exist for all those points. I think so far it's continuous and differentiable. So part A, I would say yes. Part B, find some points. So let's go ahead and find the slope of the secant and set it equal to the slope of the tangent. And we already found the slope of the tangent. It's the derivative. But the slope of the secant would be f of b, the ending interval, minus f of a all over b minus a. So here's a little bit of trig. So we know that the sine of pi/6 is nice, 1/2. So the sine inverse of the 1/2 will be pi/6. And that's the first thing that they're asking for. Plug in a 1/2 right here and tell me what is that sine inverse of 1/2. And it turns out to be pi/6. And then if you plug in a 0, the sine inverse of 0 is 0. All divided by 1/2. Instead of dividing by a half, you can multiply by the reciprocal. So that turns out to be 2 times pi/6, or let's just write that as pi/3. So I'm going to set pi/3, the slope of the secant, equal to the slope of the tangent, and solve for x. And probably the easiest way to do that is just take the reciprocal of both sides. So 3 over pi is equal to 1 minus x squared over 1, which I'm not going to write. Subtract 1. Oof, I could get a common denominator here. Oh, wait a minute, I have the wrong derivative. This is the square root. Yeah, let's see. Oh, jeez, I dropped it. I made my mistake. So I better square this thing first. So this becomes, oops, let's go this, 9 over pi squared is equal to 1 minus x squared. Now let's subtract off the ones. And again, should we find a common denominator by making this pi squared over pi squared, or just leave it? Oh, let's flip this around. 1 minus, we'll see, and then we'll take the square root of that. So you might think plus or minus, but again, I think I'm only interested in the positive values because the interval is between 0 and 1/2. So instead of saying plus or minus, I think I can just say positive 1 minus 9 over, and I might want to clean that up. We'll see what the author did, but you could find common denominators and rewrite that. But again, what you found is some x coordinate. It's a horrible x coordinate. The square root of 1 minus 9 over pi squared. And then you could go find me the y value by plugging that back into the function. Go to the function and let x be that. Let's see what how far the author did. So that's the derivative. Where was the answers? Oh, so he just left it. C is the square root of 1 minus 9 over pi squared. Good. So according to this graph, it kind of looks like the slope of the sec is equal to the slope of the tangent. This isn't a very good graph, but this is around 0.297. So somewhere in here is the actual point, but you would have to zoom in to get a little bit better graph. Evidently, there's some separation here and here, but here's the actual point. So this would be hard to tell just by graphing, and that's not the point. You want to demonstrate the calculus as well. I'll leave you with 23. Again, good practice, and 31. If you have any questions, feel free to email me. Thanks.